This machine has never touched a river, a well, or a single water pipe, yet water is pouring from its spout, drop by drop, right now. It pulled every one of those drops straight out of humid air. No pipeline, no reservoir, no aquifer buried underground for miles. Just a compact unit quietly turning ordinary humidity into drinkable water. Millions of homes without reliable water could run on air alone. Hit subscribe because your next glass of water might come from air. "43 million Americans pull their drinking water from a well they alone are responsible for. Nobody at the federal level tests that water, and almost 1 in 5 wells fails safety limits. Most families never test their own supply, so bad water can go unnoticed for years. Nitrate from farm runoff, arsenic, and lead are the most common contaminants found in tainted wells. Aquifers beneath many of these homes are dropping faster than rainfall can refill them, so homeowners are left staring at a dry pump, wondering where their next glass comes from. Drilling a new well can cost homeowners $50,000 to $100,000. Bottled water fills the gap for many, but it adds plastic waste and a steady monthly cost. Yet there is another source of water sitting above every single one of these homes. The air itself is carrying moisture, even on days that feel completely dry. Cool that air down far enough and the moisture inside it turns back into liquid. That exact temperature is called the dew point, the moment vapor becomes visible water. Your own windows do this every morning, fogging up as warm air meets cold glass. Long before machines, coastal communities in Chile's Atacama Desert strung nets to catch fog and drip water. In 1902, engineer Willis Carrier patented the first mechanical dehumidifier built on this same idea. For decades, that condensed water was treated as waste and simply drained away. Eventually, engineers asked a simple question: why not purify that water instead of dumping it? That single question is what turned an ordinary dehumidifier into an atmospheric water generator. Companies like WaterGen, Source, and Aquaria already sell versions of that same idea to homes directly. Modern units refine that same cooling cycle with sensors, multi-stage filters, and UV sterilization built in. The result is a compact appliance that turns humid air into water safe enough to drink. Next, we open one of these machines up to see exactly how it works. Inside the home AWG unit, a fan constantly pulls in outside air through an intake filter. That filtered air passes over a chilled coil, the same coil found inside a refrigerator. A compressor keeps circulating refrigerant, dropping that coil's temperature below the air's dew point. Water vapor in the air condenses on the cold coil, exactly like droplets on cold glass. Those droplets collect and drip down into a sealed holding tank inside the unit. From there, the water still isn't ready to drink straight out of that tank. It passes through a carbon filter that strips out odors and any physical particles. Next comes UV light or ozone treatment, killing bacteria before the water gets stored. A final mineral cartridge adds back trace minerals for taste and healthier drinking water. Only then does the water reach the dispenser, safe and finally ready to pour. Energy use varies a lot. Efficient compressor units run under 1 kilowatt-hour per liter produced. Desiccant units can cost more energy per liter since heating that material takes real power. Output scales with size too. Countertop units make around 8 to 10 gallons a day. Larger whole home systems can produce over 100 gallons daily under good humidity conditions. Every one of these steps depends on a single condition: how much moisture is actually in the air. Most home units perform best between 32 and 40% relative humidity. Drop much lower than that, and condensation slows down or stops producing water entirely. That's exactly why drier regions need a different design, the desiccant-based generator. Desiccant units use salts or gels that chemically grab water vapor instead of cooling air. Heating that material later releases the trapped water, which then gets condensed and filtered. This isn't just consumer tech either. The military has used real versions of it too. Some units skip the wall outlet entirely, running instead on solar or wind power. That option matters most in disaster zones or homes far from any power grid. In 2017, Hurricane Maria tore through Puerto Rico, destroying the island's water and power systems overnight. Communities were left without clean water for weeks, some for months, waiting on relief. One veteran-turned-engineer was already building a machine meant for exactly this kind of crisis. Moses West served in the U.S. Army before turning his attention toward water scarcity at home. In 2015, he founded a company built entirely around one machine, the atmospheric water generator. When Hurricane Maria hit, West brought a solar-powered AWG straight into the disaster zone. That single unit ran on sunlight alone and helped supply roughly 15,000 people with water. No fuel truck, no rebuilt pipeline, no waiting on the power grid to come back online. Just air, sunlight, and a machine quietly doing the job broken infrastructure couldn't. The foundation runs entirely on donations, and it's led by a disabled minority veteran himself. A newer deployment even reached Trinity University in San Antonio, Texas, far from any disaster zone. West's foundation later brought the same technology to Flint, Michigan's ongoing water crisis. Today, the technology has reached multiple U.S. states and several countries facing similar water gaps. In 2022, as war damaged Ukraine's water systems, his foundation raised funds to send AWGs there. Russian strikes had left millions without safe water, some hiding in basements without any supply. An atmospheric water generator could run in that basement and still produce something to drink. The foundation says altogether it has produced more than 6 million gallons of water. Compare that to a diesel generator trucked in for weeks burning fuel that eventually runs out. And solar-powered AWG just keeps running day after day as long as the sun and air cooperate. None of that solved the disasters themselves. The storms still hit, the wars still raged, but in each of those places, it meant one less thing standing between people and water. So how does this actually compare to what people are already paying for water? Over a 10-year lifespan, an efficient home unit can cost as little as 27 cents per gallon. That number includes the electricity, the filters, and the equipment itself, all averaged out. Compare that to a basic gallon of bottled water running about 80 cents to $1.50. Buy it bottle by bottle instead, and that price can climb past $9 a gallon. Even before counting a single environmental factor, the machine already wins that math. A basic home AWG unit typically costs between $1,000 and $2,500 upfront. Solar hydro panel systems run a bit higher, closer to $2,500 to $3,000 each. Either way, that's a fraction of the $50,000 to $100,000 a new well can cost. Zooming out, market analysts project steady growth for this industry through the early 2030s. Exact estimates vary sharply between research firms, so treat any single number with some caution. Most of that growth is concentrated in Asia-Pacific, where water stress runs deepest. In November 2025, one manufacturer added AI-driven monitoring that cut running costs by roughly 35%. Jal Jeevan Mission in India is pushing rural adoption forward, aiming to connect every household to safe water. Humid island nations across Southeast Asia are proving especially strong markets for this exact technology. North America still leads current adoption, partly driven by military and government purchases. The Department of Defense has procured these systems for the same reason Moses West did, running water without depending on a single fixed supply line, no matter what happens to it. That military use case says a lot about where this technology genuinely excels. It is not a fix for the driest places on Earth, but for wherever pipelines can't reach. Across the industry, cooling condensation units make up more than 99% of total revenue right now. Desiccant models remain a small niche, mostly reserved for the driest, least humid environments. Newer commercial models even report their own maintenance needs remotely through built-in sensors. This doesn't replace a desalination plant or a city's entire municipal pipeline network, but for a single home, a remote clinic, or a shelter, the math already works today. The technology clearly works, and it's priced reasonably, but is it actually well regulated? Honestly, there's no dedicated federal framework specifically covering AWG-produced water. Municipal top water is regulated by the EPA, covering more than 90 known contaminants. Bottled water gets its own separate rulebook, enforced instead by the FDA. Water pulled from air falls into neither category, with no dedicated national standard. The EPA's own research division actually tested water from a real commercial AWG unit. Researchers found no contaminants above the agency's usual health-based drinking water limits. But they also found elevated bacteria counts, a warning sign for potential regrowth. That doesn't mean the water was dangerous, but it means upkeep genuinely matters. Manufacturers can voluntarily seek independent certification, but nothing legally requires them to. That means real water quality can vary meaningfully from one brand to the next. Right now, consumers mostly have to trust the label instead of a uniform government rule. There's also a harder question sitting underneath all of this technology. Families most likely to have contaminated or failing wells often have the least spare cash. $1,000 to $2,500 is real money for someone already struggling to afford water. Without financing or subsidy programs, this risks becoming a fix mainly for people who can already afford it. Some public health advocates argue government assistance should treat these machines like basic water infrastructure. Others worry cheap subsidies just paper over pipes and wells that should be properly fixed. There's an environmental wrinkle, too, buried inside the machine's own mechanics. Compressor-based units rely on refrigerants, the same chemicals used in home air conditioners. Some of those refrigerants are potent greenhouse gases if they ever manage to leak out. Manufacturers are shifting toward lower-impact refrigerants, but not every existing unit is caught up. None of these concerns erase what this technology has already proven it can do. Real people in Puerto Rico, Flint, and Ukraine drank water this exact process produced. But proven to work and properly regulated for everyone are two very different claims. The technology simply arrived faster than the rules built to standardize it. Right now, that gap between innovation and regulation is where the real work sits. Closing it will decide whether this promise reaches beyond just the earliest adopters. Water scarcity used to mean drilling deeper, trucking in bottles, or simply doing without. This machine offers a different answer entirely: the humidity already surrounding every one of us. It won't replace desalination plants or fix an entire region's drought on its own, but for a home, a clinic, a shelter, or a soldier far from any pipeline, it already works. The next lifeline after disaster might not be a truck of water, it's the air. Hit like, share this with someone, and subscribe to SynthCosmos. We cover the science reshaping our world as we know it, every single week. We'll see you in the next one.